This is my creative assignment 2 for dynamics, and today I'll be talking about rolling. We'll be covering rolling constraints using the two-point velocity theorem, analyzing the forces involved in a rolling cylinder, considering the moment of inertia, and finding the unknowns. Let's imagine a cylinder with points A and C. To understand what it means to roll, consider what it means for it not to. If points C and A were moving at some velocity, the cylinder would be sliding along without rotating at all. In the rolling case, there is no sliding, so the velocity at A must be counteracted by a frictional force. Introducing this force prevents sliding. And finally, the constraint that rolling must abide is that velocity at point A is 0. Moving on to what we can deduce from the knowledge that velocity at point A is 0. Let's define an angular velocity theta dot and a vector from C to A. These values can be used in the two-point velocity equation, which relates the velocity of 2 points along a body. Velocity at A is equal to the velocity at C plus the angular velocity crossed with the vector from C to A. The velocity at A is known to be 0. The angular velocity only has a k component of negative theta dot due to our direction of rolling being to the right, and the radius vector only has a j component of negative r. This solves out to suggest that x dot, the velocity of C in the x direction, is equal to radius times theta dot. By taking another derivative with respect to time, we can reach another expression for the acceleration. These terms will be useful in solving for rolling behavior of cylinders. Now, let's consider the forces involved in a cylinder rolling down an inclined plane. First, gravity is acting straight down on the center of mass. It is at the magnitude mg. Next, the normal force counteracts the force normal to the surface, which is represented here as N. Friction is a little tricky because the typical formula mu times N is only applicable when friction is at its max. If friction was at its max, then unless conditions are absolutely perfect, the cylinder would be slipping. Rolling implies that there is no slipping, so friction is for now just F. Recall that the sum of moments is equal to the moment of inertia multiplied by the angular acceleration. A small adjustment is to be made though, since our theta dot is defined to be negative. Therefore, our sum of moments is instead the negative of the moment of inertia multiplied by the angular acceleration. This equation will serve useful as we continue to analyze rolling cylinders. Now, let's consider the equations that we know and try to deduct the values that we don't. We defined a new coordinate system, x prime and y prime, to make these calculations easier. Let's start with the sum of forces in the x prime direction equaling mass times acceleration. The sum of forces is mg sine phi minus the frictional force, and this equals mx double dot. The sum of forces in the y prime direction is equal to 0. This is the normal force minus mg cosine phi. The sum of moments is equal to the negative of the moment of inertia times theta double dot. The sum of moments is negative Fr, and the moment of inertia and theta double dot is as was defined on the left side of this arrow. Lastly, we have the first assumption that we made about rolling objects, being that x double dot is equal to r theta double dot. By looking at these four equations, our only unknowns are f, x double dot, n, and theta double dot. This is perfect. There's 4 equations and 4 unknowns. From here, you can plug this into a matrix, you can plug this into MATLAB, or solve this by hand to deduce the values that you need to find. The takeaways from this lecture are that rolling objects do not slip, that the two-point velocity theorem relates angular velocity to velocity. And lastly, by considering forces, moments, and the relationship between acceleration and angular acceleration, enough equations are available to solve for useful values in a problem involving rolling cylinders. Thank you for watching.